Blocks A, so mass 2.5 kilograms, and B, mass 7.3 kilograms, move on a frictionless horizontal surface. Block A is initially moving toward block B with a speed of 3.7 meters per second, while block B is moving toward block A at 1.25 meters per second. Both blocks are equipped with ideal spring bumpers. The collision is head-on, so all motion before and after the collision is along a straight line. Find the maximum energy stored in the spring bumpers. Let's draw a picture. So we have A, and it's moving with a speed initially of 3.7 meters per second. So I'm going to call this VA1. And we have block B moving towards block A with a speed of 1.25 meters per second. I'm going to define the positive x direction to be to the right. So that means VB1, since it's to the left, is going to be negative 1.25 meters per second. All right. And both the blocks are equipped with ideal spring bumpers. So it looks like this. Okay. So I'm going to call this 1. Okay. And then they collide head on like this. And they reach a point where the springs reached its maximum compression. So that's where we have the maximum energy stored in the spring bumpers. So that's this point right here. So I'm going to call that 2. And they're going to be moving together at some velocity, let's say v2, that we don't know right now. We're trying to find the maximum energy stored in the spring bumpers. So that's basically the same thing as the maximum elastic potential energy. So we have to use energy conservation. At 1, what kind of energy do we have? Do we have any gravitational potential energy?
It doesn't look too high and mighty to me.
Yeah, this is all basically at y equals 0, so we don't have any gravitational potential energy. We definitely have kinetic energy, right? Because both the blocks are moving. So we have Ka1 plus Kb1. And we don't have any non-conservative forces because it's a frictionless horizontal surface. And the normal force, is perpendicular to the displacement, so that does no work. So we just have kinetic energies. At 2, we also have kinetic energy of this system here moving at a velocity v2. So we have kinetic energy. I'm going to call that K2. And no non-conservative forces. But we also have the elastic potential energy right here because at 2, we reached the maximum elastic potential energy. So I'm going to call that US max, S for spring. All right. And that's all we got. Ka1 is 1 half MA BA1 squared. KB1 is 1 half MB VB1 squared equals K2. And remember, for 2, the blocks are moving together. So it's 1 half MA plus MB V2 squared and plus US max, which is what we're trying to find. To find US max, I just have to subtract this term from both sides. So you get US max equals all of this right here minus K2, this right here. Okay, so we have the masses of the blocks. We have the initial velocities. So the only thing we don't have is V2. How are we going to find V2? Let's ask ourselves, is momentum conserved? To know if it's conserved or not, we have to ask ourselves, is there a net external force? The blocks are applying forces to each other, so that's internal, that's fine.
This is a frictionless surface.
It's frictionless, so we don't have that. We have 2 external forces. We have the force of gravity and we have the normal force from the surface.
They cancel out.
But they cancel out. So there's no net external force. So yes, momentum is going to be conserved. So let's do conservation of momentum from 1 to 2. So remember, momentum is mv. So PA1 is MA VA1. PB1 is MB VB1. And at 2, they're moving together. So the total mass is MA plus MB, and they're moving with the velocity V2. So great, we can easily find V2 now by dividing both sides by MA plus MB. So you get this. So I can substitute that into the energy equation and I can find the maximum elastic potential energy. Okay, so we have all of this. And I'm going to factor out the 1/2 also. And V2 is this. And we're squaring all of that. There's one thing I can do to clean things up a little. I see MA plus MB, and I'm dividing that by MA plus MB squared. So one of those MA plus MBs will cancel out. So the numerator will be squared, and the denominator will just be to the power of 1 now. And we have everything, so now I can just plug everything in and we'll get our answer. So when you plug everything in, you'll get this. When you plug everything in to your calculator, you'll get that the maximum elastic potential energy is about 22.1 joules.
Think of all the things you could do with those joules.
Lots of stuff. Last question for today. Find the velocity of each block after they have separated and the springs return to their natural length. Let me draw after they separated what that looks like. So I'm going to call this 3. Okay, so this is after the blocks have separated, and we're trying to figure out the velocity of each block after they separated. So we want VA3 and VB3. So should we look at energy and momentum conservation from 1 to 3 or 2 to 3? That's what we got to figure out now. It turns out you can actually do either, but it's easier to look at 1 to 3. So basically before and after the collision instead of 2 to 3. And then again, the positive x direction is to the right. So the momentum is going to be conserved from 1 to 3, right? Because there's no net external force. So the left-hand side is MAVA1 plus MBVB1. And the right-hand side is the same thing, but the velocities are VA3 and VB3. So we have one equation with two unknowns. We don't know VA3 and we don't know VB3. So we need another equation. And that equation is going to be the conservation of energy equation. By the way, what kind of collision is this?
This seems to me quite elastic.
Yeah, it looks like an elastic collision. So before and after the collision, kinetic energy should be conserved. So let's see. At 1, we only have kinetic energy. We have KA1 and KB1, just like we saw last time. And same thing at 3. There's only kinetic energy. So we're basically at y equals 0, so no gravitational potential energy. The springs are not in contact with each other. They're both at their natural length, so there's no elastic potential energy. And like I said, the normal force does no work. So it's just kinetic energy is being conserved. So we have KA1 plus KB1 equals KA3 plus KB3. So KA1 is 1/2 MAVA1 squared. KB1 is 1/2 MBVB1 squared. And same thing for KA3 and KB3, except the velocities are now VA3 and VB3. And I can multiply both sides by 2 and get rid of all these 1/2s. So you'll get this. We now have two equations with two unknowns, VA3 and VB3. So let me plug in some numbers and see exactly what these equations look like. So when you plug in all your knowns for both equations, you're going to get this. And when you do all the arithmetic, you're going to get that the first equation is a linear equation, it's 2.4 VA3 plus 7.3 VB3 equals negative 0.245. And if you do all the arithmetic for the energy conservation equation, you get 2.4 VA3 squared plus 7.3 VB3 squared equals 44.26225. All right, so like I said, we have two equations with two unknowns, but the thing is, they're not both linear equations. This second equation here is a nonlinear equation. Let me actually put these in red. You can use substitution to solve these equations. You can isolate one of the unknowns and substitute in the other equation, but it takes a while, takes a good amount of algebra to do that. A lot of physics exams allow graphing calculators. So what I would recommend is graph both of these equations and see the intersection points. So this is going to be a line, and this equation right here, it's nonlinear, and it turns out it's an ellipse. So if you graph it, it's going to look like this. So you get two solutions, and we're going to use this solution where VA3 is negative and VB3 is positive because A is moving to the left after the collision and B is moving to the right after the collision. So it turns out the solution using the graph is that VA3 is about negative 3.75 meters per second and VB3 is about 1.20 meters per second. That is it for today. So make sure to comment what you think, and I'll see you guys in the next video.